Okay, the first chapter in electricity is about static electricity. First, we know the basic ideas of charges or the basic rules of charges that like charges repel. So positive and positive repel, negative and negative repel. Unlike or opposite charges attract. So positive against negative, they attract each other. And as the distance between the charges increases, the force between the charges decreases. Force increases when distance decreases. But where do these charges come from? From the protons, neutrons, and electrons. Neutrons are neutral, electrons are negatively charged, protons are positively charged. When transferring charge from an object or to an object, we say that it will be positively charged or negatively charged, but only negative charges can be transferred. Only electrons can move. So a positively charged object, it lost electrons. A negatively charged object, it gained electrons. You cannot say that you add protons or lose protons. Only electrons can move. For the materials or types of materials that are considered when dealing with electricity, we say that there are good conductors, poor conductors or insulators, and semiconductors. A good conductor is a material that allows the flow of charge or flow of electrons. An insulator is a material that does not allow flow of charge or flow of electrons. Or we can say that conductors have free electrons, insulators do not have free electrons. Semiconductors are good conductors when heated or when there is a large amount of light incident on them, but poor conductors in cold temperature or dark environment. If you want to charge something, there are several methods. The first method is by friction or rubbing, but you must use poor conducting materials. For example, plastic and wool or glass and silk. It only works with poor conducting materials because good conducting materials lose the charge as soon as they get the charge. They lose charge quickly. So if you are asked why friction charging does not work on metals, for example, you say that metals are good conductors, so they lose the charge quickly. They gain charge, but they lose it quickly. But for poor conductors, if they gain charge, they keep the charge. For example, if you rub two materials, one will get a negative charge and one will get a positive charge. The one that gained negative charge means that it gained electrons, and the one that gains positive charge, it means that it lost electrons. So here the cloth lost electrons to the rod. And finally, the amount of negative charge on the rod is equal to the amount of positive charge on the rod if they started as neutral objects, because neutral means the amount of positive is equal to amount of negative. For other materials, the rod can be charged positively and the cloth might be charged negatively. That means that the electrons moved from the rod to the cloth, and still the final charge, positive and negative, will be equal if the initial charge was neutral. The next type of charging is by contact, and it must happen with conductors. So you must have free electrons to flow between two objects and they share the charge. For example, if you charge a neutral object with a positive object, both will become positive. If you touch a neutral object with a negative object, both will become negative. They share the same charge. The last type of charging is charging by induction. You can first separate the charge inside a good conductor, not an insulator. So contact charging is with conductors. Induction charging is using also conductors. You can separate the charge by bringing a charged object near a conductor. If you place a positively charged object near a conductor, the free electrons will move towards it. If you place a negatively charged object near a conductor, the electrons will move away from it and leave the other side positively charged. You cannot say that the positive charge is attracted or repelled. Only electrons are moved or negative charges moved, leaving the other side positively charged. So this is a way you can separate the charge. This can happen in poor conductors, but not as much as good conductors. The induction only works best in good conductors. Sometimes you are required to say what will you do next to make the object charged. You only separated the charge inside the object, but still the amount of charges, positive and negative, in the object are still the same. So the object is still neutral. But to continue to charge the object, there are several steps. So step 1, bring a charged object near the conductor. Step 2, connect the conductor to the ground or to earth, or earth the conductor. Step 3, remove the ground connection. Step 4, remove the charged object. So first, you bring a charged object near the metal or the conductor, then you connect the metal or the conductor to the ground or earth, then remove the earth connection, then remove the charged object. What happens if you remove the charged object before the ground connection? It will not be charged. It will remain neutral. But what happens if you earth a charged object? It will become neutral. So these steps, you start with neutral and you end with charged. But it is always the opposite charge. If you bring a positively charged object, you will get a negatively charged metal. If you bring a negatively charged object, you will end up with a positively charged metal, using the same 4 steps. But if you start with a charged object, for example, a positively charged object, it has more protons than electrons. If you connect it to the ground sends electrons that will neutralize the positive charge. So it becomes negative. And if you connect a negatively charged object to the ground, it will also be neutralized, but in this case, electrons will move from the object to the ground. Another example, if you have 2 metals in contact and you bring a positively charged object near one of them, electrons will flow towards the positively charged object, leaving the other object positively charged. So since there is contact, so electrons were able to move from one object to the other. So one object will become negative and the other object will become positive. You must also remember that the number of negative charges and positive charges must be equal. If you separate the 2 objects, the one that became negative cannot lose the electrons, and the one that became positive, it cannot gain electrons. So this will remain negatively charged and this will remain positively charged. There is no earthing required in this case. Now, how can we calculate the charge on an object? The charge we call Q is equal to the number of electrons, which we call N, multiplied by the charge of 1 electron. This charge of 1 electron we call E, and it is equal to 1.6 times 10 to the power of negative 19, and the unit is coulombs. This number is not required to be memorized. It will be given in the question, or you are required to calculate it, but in this case, you must be given the charge and the number of electrons. Or you can be given the total charge and the charge of 1 electron, and the number is required, so N will be equal to Q over E. And N has no units, Q and E have the same unit, which is coulombs. Now, as for the dangers of static electricity, if you have too much charge on an object and you bring another neutral object near it, there will be a spark. This spark can cause a large current to flow. For example, in the case of clouds, when wind rubs against the clouds, they get charged by friction. Then they release the charge either between each cloud or from the cloud to the ground. This current is very high and can actually cause a lot of damage due to the high temperature of the current. Or the spark you experience when you touch the handle of a car, or in the case of an airplane, the charge will be much greater since the body of the plane can carry much more charge. So at first, before fueling a vehicle or a plane, you must earth it to remove the charge to avoid the sparks to happen during the flow of fuel, because fuel is flammable and any spark will ignite the fuel and cause it to catch fire. As for the uses of static electricity, we have the idea of electrostatic precipitators in chimneys of houses or of manufacturing factories. The charge of a high voltage power supply is given to 2 plates or 2 meshes or two metal plates. These attract the smoke and dust particles during the exit of the gases from the chimney. So you remove the solid particles from the exhaust, and you are left with only gases that come out of the chimney, no solid particles or no ash that comes out with the gases. The second application is the inkjet printer. There are two plates that are charged oppositely, and the ink that falls from the jet is negatively charged, so it is attracted towards the positive side. You can change the charge on the plates and control where the ink will fall on a piece of paper, so you can draw the shape of the text or the drawings coming from a computer. The photocopying machine follows the same pattern, only uses a drum that is charged positively, and light that is incident on the drum makes it lose charge except for the shape of the text from a paper. So light falls on a piece of paper and reflects on the drum. So the drum loses charge from the pieces of the paper that were white or bright, and it keeps the charge from the pieces that were dark. And then the ink is dropped on the drum. It only goes towards the charged part, and when you compress a piece of paper on that charged part, it gains the ink, or the ink melts on the piece of paper, so you have copied the text. The last part about static electricity is called electric fields. An electric field is a region or an area where an electric charge experiences a force. The direction of the field is the direction of the force on a positive charge placed in the field. It must be positive. So to imagine the direction of the field, say you have a source of field that is positively charged. If you place another positively charged object, it will get repelled. So the field around the positive charge is outwards, radially outwards. Since if you place any positively charged around it, it will get repelled outwards. The opposite will happen if the source of the field is negatively charged. If you place a positive charge around the negatively charged object, it will be attracted inwards. So the field around the negatively charged object is inwards, or we say that the field is directed from the positive charge towards the negative charge if you have several charges. Now the distance between the lines represents the strength of the field. So small distance between field lines means strong field. Large distance between field lines means weak field. So this field is not uniform. It has places where it is stronger and places where it is weaker. To make a uniform field where the strength is constant, we need the lines to be equally spaced at all positions. So a uniform field would look like parallel, equally spaced lines. To create that field, we need two flat plates that are oppositely charged. One charge positive and one charge negative, and the field will be parallel, equally spaced lines from one plate to the other plate, from the positive plate to the negative plate. If you have a positive charge in the middle, it will move with the field. If you have a negative charge in the middle, it will move against the field. Okay, chapter 12 is about electric circuits and electrical components. First, we need to define the potential difference. It is the energy required to move a unit charge, which is 1 coulomb of charge, from one point to another or between 2 points. And the unit is in volts. So if you have two charges that are the same, this has high energy and this has an equally high energy. So there is no energy difference between the 2 points. So there will be no flow of charge. You cannot move charge between these points. But if you have a high charge and a higher charge, or high energy and a higher energy, there is a difference in energy, so there will be a flow of charge. For example, if you place a positively charged object here, it will move in this direction. It will repel from the large positive charge and will go towards a low positive charge. Or if you have a positive and negative charges, this is high energy and this is low energy. There is a difference in potential energy, so charge will move again. So if you place a positive charge, it will move in this direction. So if there is no potential difference, there is no flow of charge. If there is a potential difference, there will be a flow of charge. Since the definition of potential difference, which we can call V, is equal to the energy per unit charge, it is equal to energy divided by charge. The charge is in coulomb, the energy is in joules, and the potential difference or voltage, it's also called voltage, is in volts. Now we define electric current or electric current intensity. It is the rate of flow of charge. Again, rate means divided by time. So the electric current, which we call I, is equal to the charge flowing divided by the time. The charge would be in coulombs, the time would be in seconds, and the current is in amperes. And you can also calculate the charge by multiplying the number of electrons by the charge of one electron. Now there is something called the flow of electrons or electron flow, and another thing called the conventional current. So if you have a conductor and there are atoms that are neutral, then you connect one side to a positive charge and then the other side to a negative charge. The electrons are repelled by the negative charge and flow in this direction. This is called an electron flow. It moves from the negative connection to the positive connection, or from the negative terminal to the positive terminal. But whenever an electron leaves its place, it leaves behind a positive charge. So the electron moved in this direction, it left behind a positive charge. Then this electron will move in this spot, in the empty spot, leaving behind another positive charge. Now the positive charge appears to be moving in the opposite direction. This is called conventional current. So in any circuit, if you have a battery that has a positive terminal and a negative terminal, the conventional current flows from the positive to the negative, but the electrons move in the opposite direction. Electrons flow from negative to positive, current flows from positive to negative. Now the battery is the source of potential difference. It created the positive and negative charges by chemical reaction, so it converts chemical energy into electrical energy and creates a potential difference. If you have a supply with a potential difference, you call this potential difference electromotive force. So to define electromotive force, it is the same as potential difference. It is the energy needed to move a unit charge, but not between 2 points. It is the energy needed to move a unit charge across a complete circuit or through a complete circuit. Now, current has several effects to prove that it is working. It can have a heating effect. Any current flowing through any object or a material or a component heats it up. The current creates a magnetic field around the component. The current creates sometimes chemical reaction if you include an acid and two electrodes that are positive and negative charges. Or if you have a lamp or a filament wire that heats up too much, it will eventually emit light. So heating, lighting, magnetic, and chemical effects. Now for any circuit to work, you need a source of EMF, of electromotive force or voltage, and you need the circuit to be closed, all connections to be tight and connected to each other. No open circuit, because an open circuit will have an air gap in the middle, and air is a poor conductor that does not allow flow of charge, which is the current we need. Now there are circuit diagrams you are required to remember. For an electric cell, you draw a large or a long line and a small line. The long line represents the positive side, the smaller one represents the negative side. For a battery, you draw several cells connected to each other, either in series or in parallel. You can draw one behind the other like this, and the connecting leads or connecting wires. For a switch, you draw this symbol, a broken line with an empty piece inside. For a connecting wire or a lead, you can draw straight lines, curved lines, or broken lines. These are wires or leads, connecting leads. For a lamp or a filament, you draw a circle with a large X in the middle of the circle and the connecting terminals. Now, if you want to measure the potential difference or the voltage across a component, you connect a voltmeter, which is drawn a circle with a V at the center, all around the component. So if you measure the potential difference across this lamp, you need to connect one wire from the voltmeter on one side and another on the other side, and you see this shape. This shape is called the branch. That means that the voltmeter is connected in parallel and there are two branches. You must close the branch from one side and the other side. If you connect an ammeter to measure the current, the ammeter does not require a branching or does not need to be connected in parallel. It is connected in series, which means you need to cut the connection and insert the ammeter in the middle. So there is only one direction to flow in the circuit, or one direction for the current to flow. In this case, the current can flow this way or to the voltmeter. This is called a parallel connection. One cycle means series, branching means parallel. You can also connect other devices in series and in parallel. If you have a series connection, you must know that in series connections, the current is the same everywhere. So these ammeters all read the same reading, but the voltage is divided. So if you have 12 volts here and you got 6 volts here, this will be 6 volts also. Or if the components are not identical, if you get 8 volts here, you will get 4 volts, just so that if you add the voltage across the components, it will be equal to the sum of the supply or the EMF of the power supply. So voltage is divided in series, current is the same in series. In parallel, it is reversed. The current gets divided, so the charge moves in this direction. Once there is a branch, the current can either flow this way or that way, so it is divided. So you have several currents. So you have the current in the battery or the supply, and you have the current in the first lamp and the current in the second lamp, or first branch and second branch. The total of these two currents is equal to the current in the power supply. So current gets divided, but the voltage is the same. So if this is 12 volts, this is also 12 volts, this is also 12 volts. So if you get two components connected in parallel, each having 6 volts because they are connected in parallel, the total voltage will not be 12, it will also be 6. The total voltage is the same as the individual voltage. There are advantages of using parallel connections over series, is that each branch can work independently. It can have its own closed circuit. It does not depend on the other branches, and that it takes the full voltage of the supply, so the current will be higher. The only advantage for a series connection, it is not repeated many times in the questions in the past papers, but the only advantage of a series connection is that you will have low current, so the battery life will be longer. If you connect batteries in series, the voltage will be added together. So if you have a 1.5 volt cell and you connect two of them in the correct way, which means positive, negative, each terminal has an opposite terminal facing it. So the total voltage will be 3 volts. But if you connect one of the terminals in the wrong position, so for example, negative facing negative or positive facing positive, the voltage will actually decrease. So the first one will increase the voltage by 1.5, the second one will increase the voltage by 1.5, and the last one will decrease the voltage by 1.5. So you lost this voltage by adding one battery in reverse. So the voltage will be only 1.5 in this case. Connecting batteries in parallel does not change anything in the circuit or the voltage. So if you have 1.5 volt cell, 1.5 volt cell, and you have a battery of two connected in parallel, the total voltage will still be 1.5. Since the supply voltage did not change, the circuit will have no change in current or voltage or anything. Now for a quick example, you have a total voltage from a supply 18 volts and the current coming out of the battery 5 amperes, and you have one lamp here, lamp 1, two lamps connected in parallel. We consider this whole area, to be connected in series with lamp L1. Now, how did we know that lamp 2 and lamp 3 are connected in parallel? We saw a branch before the lamps and a branch after the lamps. So we have the voltage across one of the lamps to be 8 volts, so we must know that the voltage here is also 8 volts, and this whole section takes 8 volts. In parallel, the voltage does not get divided and it does not get added up. So 8 volts, the total is also 8 volts. So if you have a series connection, if 8 volts were transmitted to this section, the rest of the battery voltage will go to the other section. So we calculate the voltage here as 18 minus 8. So this is 10 volts. So in series, the voltage gets divided. In parallel, it does not. The current in this section is the same current coming from the battery. So 5 amperes went through this part, but at the branch, it will get divided. 2 amperes went in the lower lamp, so the rest will go in the upper lamp. So the current here is 5 minus 2, which is 3 amperes. So you get 3 amperes from the top, 2 amperes from the bottom. It connects again to form 5 amperes before the battery, and the current going into the battery is equal to the one going out of the battery. Now we go to something called resistance. Resistance is a property that opposes the flow of charge or opposes the flow of current, and the unit is ohms. Resistance is calculated as voltage divided by current. You can rearrange this equation to calculate current equal voltage over resistance, or voltage is equal to current multiplied by resistance. Whereas voltage is in volts, resistance is in ohms, and current is in amperes. The resistance of any conductor depends on 3 things: its length, its cross-sectional area or diameter, and its material. The material is not required in the IG syllabus. There is something called resistivity. You are not required to know that. It's about AS level. Nothing will be asked about resistivity in O level. So you will always see 2 wires made of the same metal, 2 wires made of the same conducting material, because the material is not included in the syllabus. But you should know that the resistance is proportional to the length, and that the resistance is inversely proportional to the cross-sectional area. And since area is equal to pi r squared, or the diameter squared over 4, if the diameter is multiplied by a number, the area will be multiplied by that number squared. So if you have diameter times 2, the area will be times 2 squared, which is 4. But since resistance is inversely proportional to area, the resistance will be divided by that number squared. So resistance will be divided by 4. So if the length is multiplied by 3, resistance is multiplied by 3. If area multiplied by 3, resistance will be divided by 3. If the diameter is multiplied by 3, area is multiplied by 9, 3 squared, and the resistance will be divided by 9, 3 squared. You can also use equations as ratios. If you compare 2 wires with different resistances, resistance 1 and 2, this ratio will be equal to the ratio of the length, 1 to 2, multiplied by the reverse ratio of the area, which is area 2 to area 1. Or you can replace the area with diameter, diameter 2 over diameter 1, but you will have to square this bracket. So R1 over R2 is equal to L1 over L2 times A2 over A1, or L1 over L2 times D2 over D1 all squared. Now we have 2 types of something called resistors. We have fixed resistors, which can also be called just resistors. The symbol of a resistor or a fixed resistor is a rectangle with terminals. This has a constant value of resistance, which means it is made of a certain material that has a constant length and constant cross-sectional area, and its resistance does not change. For a variable resistor, we use an adjustable length. So we have constant material, constant cross-sectional area, but the length can be increased. If you move a slider this way and you connect the circuits to these 2 parts of the slider, as you move to the right, the length used from the wire will increase and the resistance will increase. So length increases, resistance increases. If you move in the opposite direction, the amount of wire used in the circuit will be less, so the resistance will be less. This is called a variable resistor, a potential divider, or a rheostat. They are all the same, and they have 2 symbols. The first symbol is a rectangle with an arrow across it. The second symbol is a rectangle with 2 terminals, but one connected in the circuit, which is this one, and the other side is left open, and a slider on top that can change the direction of motion or the length of the wire. So you either use this symbol, rectangle with an arrow across it, or two terminals, one connected and one left open, and a slider, a pointer with an arrow from the top. That is the other connection in the circuit. Now there is something called Ohm's law if you use a fixed resistor or something called an ohmic conductor. If you change the voltage and current across this type of conductor, you will get a graph that is a straight line through the origin. This means that the voltage and current are directly proportional to each other. So if you're required to state Ohm's law, you state that the voltage is directly proportional to the current across a conductor that has constant temperature. That's what fixes the resistance. If you have a filament wire, the graph will be a curve that tends to bend towards the voltage axis. If you reverse the axes, if the voltage is on the x-axis and the current is on the y-axis, the curve will be pointing in this direction. For a filament wire or a filament lamp, as current increases, temperature increases, so resistance increases. If you're required to explain this, temperature increases as current increases, so resistance increases. So more voltage is needed, or more energy is needed. Now for connecting resistors in series, still voltage gets divided, current remains the same, but if you want to calculate the total resistance, you add the resistors together. But if you want to use V equals IR or R equals V over I, you must balance the equation at that section of the circuits. For example, for this circuit, V1 is only equal to I times R1, V2 is only equal to I times R2, and so on. If you want the total voltage is equal to the total current to the total multiplied by the total resistance. So it is local or total. You cannot use the whole voltage for all components because voltage is divided. You cannot use the total resistance for all components since you might have different resistors, and the total resistance is not the same as each individual resistance. In parallel, the voltage is the same, the current gets divided. If you want to calculate the total resistance in parallel, you can either use 1 over the total resistance is equal to 1 over each resistor added, or if you have two resistors in parallel only, this only works with two resistors, you can say that the total resistance is equal to the product over the sum. But this only works for two resistors in parallel. You cannot use it with more than two resistors in parallel. Just a reminder, when calculated using the original equation 1 over the total resistance, at the end of your calculation you must calculate the reciprocal. So you calculate 1 over something plus 1 over something and so on. After you finish and you press equal, you must press 1 divided answer or answer to the power of -1 to get the reciprocal. You calculated 1 over the resistance, not the resistance. To get the resistance, you get the reciprocal by using 1 divided answer on the calculator or answer to the power of -1 on the calculator. Or if you can calculate using this equation, you get the resistance directly, but this only works with two resistors in parallel. Now, if you have resistors connected in series or you have a variable resistor connected like this, we call this a potential divider, where the resistance is directly proportional to the voltage. The larger resistance gets the larger voltage. If a resistance increases, its voltage increases and the rest of the voltage decreases. For example, in this section from point X to point Y to point Z, if you move this slider upwards, section XY increases in length. So the resistance between X and Y increases and the voltage across XY increases. But the voltage across YZ decreases. Since the total voltage is the same, Since the total voltage is the same, if one voltage increases, the rest of the voltage decreases. For example, at first the voltage was 12 volts and it was divided 6 and 6. But since the lower part increased, the lower part became 7, so the upper part will become 5, so the total will remain 12. Now, if you connect anything in parallel with this section, the voltage will also increase across it if the resistance increases. So if you move the slider upwards, the voltage here increases and the brightness of the lamp increases. The opposite will happen if you connected the lamp on the upper part. The upper part decreases in length, so the voltage on the upper part decreases and the lamp's brightness decreases. Now, if you are calculating voltages, for example, if you have 3 ohms and 6 ohms and 12 volts, and you want to calculate this voltage, and the upper voltage is V2, you can say that the 12 volts is represented in the total resistance of 3 and 6, which is 9 ohms in series. So how many volts will be gotten by the 3 ohm resistor? You create a ratio equation or cross multiplication. You can say that the voltage V1 is equal to 12 times 3 divided by 9. The last part in this chapter is about short circuits. If you connect anything in parallel with a component and that thing is with zero resistance, the current only flows through the zero resistance and the component does not work. So if you have 2 resistors and you have a switch in parallel with one of them, and there is a battery. First, the current flows through both resistors and the circuit works normally. If you close this switch, the current will flow in this direction. It will not go through the resistance. It will only go through the one without the short circuit. So the voltage is now not divided, so the current increases. So if you add a short circuit across a component, that component does not work and the current increases. Chapter 13 is about electric power. First, we need to know how to calculate the energy, electric energy. Electric energy is calculated either using VQ, which comes from the equation of the voltage. Voltage is equal to energy divided by charge. So by cross multiplying, energy is equal voltage multiplied by charge. Or you can replace Q with IT, so VIT. This comes from the definition of current. I is equal Q over T, charge over time. You multiply by time on the other side to get the charge. The voltage needs to be in volts, current is in amperes, time in seconds, and charge is in coulombs. And the energy is always in joules. To calculate electric power, it is the same as any power. It is energy divided by time. So you have VIT divided by T. So T cancels out and you get the equation for electric power is equal to voltage multiplied by current. So the voltage is in volts, current is in amperes, and you get the power is in watts. You can also calculate the power using 2 more equations. If there is resistance involved, you can calculate power is equal to I squared, current squared multiplied by R, the resistance, or power is equal to V squared over R, voltage squared divided by the resistance. Resistance is in ohm, voltage in volts, current ampere, and power is in watt. Now for the mains electricity connections, there are 2 types of current that you can connect to anything, to any circuit. There is direct current, which is current that flows in one direction, usually supplied by a battery or a DC supply. And there is alternating current that keeps reversing direction. And this is the main or the usual type of current that comes from mains electricity or from the electric power stations and generators. For a steady direct current, you have a straight line. The current does not change with time. If you have a variable direct current, the current keeps in the same direction but varies on the y-axis. The value changes on the y-axis but is never negative. For an alternating current, there is positive voltage and negative voltage. That is when the current flows one direction and when the current reverses direction in the circuit. In a generator also, the current keeps changing value. It increases from 0 to maximum positive, then decreases to zero, then increases to maximum negative, then decreases to zero, and keeps repeating the cycle again. If you have a direct power supply, you either draw it as a battery, which is long line, short line, and so on, or two circles with positive and negative labels. If you have an alternating current supply, you draw two circles with a wave in the middle. Now for the wiring, we have three types of wires. There is a live wire which carries the alternating voltage that keeps reversing between positive and negative. There is a neutral wire which is just to connect the circuit or to complete the circuit, to make it a closed circuit, not an open circuit. And there is the earth wire which is not connected actually to the circuit. So the live wire function is to carry the alternating voltage, keeps reversing between positive and negative. The neutral wire's function is to complete the circuit. For the fuses, a fuse has a symbol of rectangle and the line across with the terminals. The fuse function is to open the circuit or to melt or blow when the current gets too high, and it is usually connected to the live wire to prevent the voltage from reaching the circuit. A switch would also be connected to a live wire, but they will work, a fuse and a switch would work just the same if they are connected to a neutral wire, but it is just safer for the user if you connect them on the live wire to prevent the voltage, not just to prevent the current. An earth wire is connected to the metal casing of an object. If the live wire touches the metal casing of the object and the user touches the metal case, a large current will flow through them. They will get electrocuted. So instead of connecting the metal to the user directly, the metal is also connected to the ground using an earth wire. So the current will have two options: to move through the person or the user, or to move through the earth wire. The resistance of the earth wire is much less than the resistance of the user, so the current flows through the earth wire. And since the resistance is very low, there will be a large current that passes through the earth wire and the fuse, so the fuse will blow. So it will prevent electrocution. Now, if you have an object that is double insulated, this means that the casing is not a metal casing. It is made of a poor conducting material, so you will not need an earth wire. Now, when connecting wires and plugs, you need to make sure that there are no exposed areas and no left out wires, or the connection must be clean, or there is a tight connection between each component and the other. If you use a fuse, you must know how much current can it take. So for example, if you have a device that can take up to 4 amperes and the connecting wires can take up to 20 amperes, the wires can take much more current, so you are not worried about the wires, you are worried about the device. The device can take 4 amperes, so you must decide on a fuse that does not allow current to flow much greater than 4 amperes, even though the wires can take 20 amperes. So if you want 4 amperes and you are left with choices, a fuse that can take 3, 5, or 13 amperes. You cannot choose 3 amperes since the current of 4 amperes will always blow the fuse. And you cannot use the 13 amperes since it is much greater than the 4 amperes. So the current can reach 13 and this will damage the object. But it does not necessarily have to reach 13. So a trick question may come that a person, instead of using a 3 ampere fuse, he used a 30 ampere fuse. What happens when you connect this fuse and switch on the circuit? Nothing happens. The circuit works normally. What is the danger? That if the current gets too high, the device will be damaged. So you choose the fuse which is just above the required value. Now, for using two-way switches, there are two methods of using the two-way switch. Either using 2 wires and 2 switches, and you can switch on from one of the switches and switch off from the other switch. If you want to switch on, both switches must be connected to the same wire. If you want to switch off, one must be connected down and one must be connected up, or connected to different wires. Or you can use one switch as an alternating switch between two branches. So you must have a parallel connection, and the other connection is not a connection, it is not a branch, it is a two-way switch. So the current will only flow through A or B. It cannot flow through both lamps. As for the dangers of mains electricity, you have a very high voltage with a very high frequency. It changes direction 50 times per second or 60 times per second, which causes electrocution if you touch the wire. And the high current may cause nerve damage. So the high voltage causes high current, and the high current may cause nerve damage. Or the high current may cause electric fires. If you create a short circuit across a high voltage supply, a very large current will flow, and this current creates a heating effect that may actually burn the wires and may cause the whole building to catch fire. Okay, the other risk of mains electricity is that you may cause electrocution if using wet environment. So electric wires around gardens and around swimming pools or sinks or tubs or in the bathroom must all be insulated. The last part in this chapter is about calculating the cost of electricity. There is a unit of electricity or electric energy called the kilowatt hour. Kilowatt is power and hour is time, and multiplying power by time you get energy. But this is not energy in joules, since kilowatt is actually 1000 watt and 1 hour is actually 3600 seconds. So if you connect a 2000 watt heater and you keep it working for 4 hours, you can calculate the energy in kilowatt hours. 2000 is 2 kilowatts and 4 hours is already ready for the equation. So you multiply power by time. So 2 multiplied by 4, you get 8 kilowatt hours. So for example, if you have the cost of the electricity or the electric bills is 0.4 pounds per kilowatt hour, you can calculate the total cost of the energy used. So you multiply 8 by 0.4, you get the total cost. Now we move on into magnetism and magnetic fields. First, we need to know that there are magnetic materials and non-magnetic materials. Magnetic materials are those that are affected or attracted by magnets and can be turned into magnets. Non-magnetic materials are materials that are not attracted and cannot be turned to magnets. The magnetic materials are only 4: iron, cobalt, steel, and nickel. All other materials are considered non-magnetic, which means if you bring a magnet near a metal that is not one of the 4, it will not get attracted. So if you place a magnet near an aluminum bar, it will not get attracted. Gold bar, it will not get attracted. Iron bar, it will get attracted. Now, there are rules for the magnetic poles. There are North Pole and South Pole. There is something called a north-seeking pole that points toward the geographical north of the Earth, and a south-seeking pole or S pole that points toward the S pole or the South Pole of the Earth. If you leave the magnet to rotate freely, it will always point in this direction. This is the idea of a compass. A compass is a magnet that is free to rotate, so it always points toward the north of the Earth. The poles are always in pairs. You cannot find a separate North Pole or a separate South Pole. You can only find pairs of poles. And the rules of poles are the same as charges. Like poles repel, north against north repel, south against south repel, but north against south, unlike poles, attract. And as the distance between the poles increases, the force decreases. But the charges are not the same as the poles. So you cannot say that a north pole would attract a negative charge. Actually, there is no effect. Nothing happens when you place a north pole near a negative charge or a positive charge. Nothing happens. A pole only affects a pole. A charge only affects a charge. To test if an object is a magnetic material or non-magnetic material, just place a magnet near the metal or the object. If there is no attraction, it is a non-magnetic material. If it is attracted by both poles from the same side, for example, if you place the north and south pole of a magnet near one side and both get attracted, that's a magnetic material, but it is not a magnet. It does not have its own north and south poles. But if you place in the north and south, one attracts and one repels, that's a magnet. If it attracts the north pole, then this is a south pole. That's why it repels the south pole from the other magnet. So a repulsion test tests if you are a magnet or not. An attraction test tests if you are a magnetic material or not. No effect. This says that you are not magnetic material at all. Now, for a magnetic field, the definition of a magnetic field is a region where a magnet, a magnetic material, or a moving charge experience a force. So a moving charge is a current, so a magnet, a magnetic material, or a current experience a force. The shape of the field can be determined using iron fillings as shown in the diagram, or by using compasses placed one behind the other, pointing head to tail from one pole to the other pole. A compass does not only show the shape of the magnetic field, it also shows the direction of the magnetic field, but iron fillings only show the shape of the field. The field is to be drawn correctly. It must be oval, not circular curves, pointing from one pole to the other pole. It is always pointing from the north pole toward the south pole. If you're asked what is the meant of the direction of the magnetic field, it is the direction of the force on a free north pole in the field. How would a compass point in the field? It always points tangent to the field line and in the same direction as the field line. These field lines are always close to each other at the poles, and they get wider apart going further away from the poles, and you must always make sure that these lines do not intersect, do not start from the same point, and they are not parallel to each other. If you have two opposite poles, you create in between a uniform magnetic field. If you have two like poles, you leave in between a neutral zone, where there will be no magnetic field or no resultant magnetic field. If these poles were reversed as south poles, the arrows will be reversed, not pointing away from the poles, they will be pointing towards the pole. Now, why does a compass always point upwards or towards the north pole of the Earth? Because the north pole of the Earth is actually a south magnetic pole. So the geographic north of the Earth is actually a magnetic south pole of the Earth. That's why the N side of a compass points towards it. And the S side of the compass points down there, which means that the south geographic pole of the Earth is actually a north magnetic pole. So the field points away from the bottom towards the top of the Earth. Now, how to magnetize a steel bar or to make a permanent magnet? You can use one of three methods. Induction, which means just place it near a magnet or just place it next to a magnet. A north pole will create a south pole right next to it, leaving the other side north, or a south pole will create a north pole right next to it, leaving the other side south. This is called magnetizing by induction. Or you can use stroking, which using one pole of a magnet and rubbing against one material, attracting the other pole of the material towards that direction. So if you use a north pole and move to the right, the last position you move from will be a south pole. The north attracts a south. Then you move away and repeat the motion again and again and again and again, arranging more poles towards one side. So induction charging and stroking create weak magnets. If you want a strong magnet, you use a solenoid connected to a direct current supply. You place the steel bar inside the solenoid, switch on the current, then switch off the current. The steel will become magnetized. If you use an alternating current, it will still be magnetized, but not as strong as a direct current. If you want to demagnetize a magnet, you can use hammering, heating, dropping, or passing the magnet through a solenoid with an alternating current inside it, but using an orientation east-west. Actually, it will not matter, but if you are asked to demagnetize east-west, if you are asked to magnetize, it is north-south, because the magnetic field north-south with the earth, it helps magnetizing. Perpendicular to the earth, it actually does not help magnetizing. So for magnetizing, direct current switch on and switch off with the steel inside. For demagnetizing, an alternating current kept on during the whole thing and pass the magnet through. It will come outside from the other side unmagnetized or demagnetized. Or you can use an alternating current and keep changing the current magnitude. Use a variable resistor to change the current while the steel bar or the magnet inside. If you keep changing the alternating current with the magnet inside, it will be demagnetized. One more thing, if you choose steel to make a magnet, you will create a permanent magnet. This is called the hard magnetic material. It is hard to magnetize and hard to demagnetize. If you use a soft magnetic material like iron, it is easy to magnetize. Once you remove the magnetizing method, it will lose its magnetic poles. Next chapter is about the magnetic effects of a current. If you place a compass right next to a wire and then you switch on the current, you will find that the compass changes direction. If you explain this, you would say that the current creates a magnetic field around the wire. This magnetic field is circular or concentric circles if you use a straight wire, or it is more like the magnetic field of a bar magnet if you use a coil or a solenoid. If you want to know the direction of the current, you use something called the right hand grip rule, and you know the direction of the current from the connections of the battery, or it will be mentioned in the diagram or in the question. So if you use the thumb as a pointer of your right hand in the direction of the current, your fingers will curl in the direction of the magnetic field, which in this case, if the current is going down, the fingers are curling clockwise, so the magnetic field is concentric circles going clockwise. If you reverse the battery, you reverse the current, so the magnetic field is reversed. If you point with the thumb pointing upwards this time, your fingers are curling anti-clockwise, so the field is concentric circles going anti-clockwise. Now, to make sure that you draw the field correctly, you need to draw at least 3 lines. So the 3 lines are 2 close to each other and close to the wire, and 1 with a larger spacing to represent that the strength of the field gets weaker as you move away from the center of the field or the wire which creates the field. And pointing towards the inside of the page means that there will be an arrow pointing upwards but inclined. So this is current into the page. An arrow pointing downwards but inclined means that the current is going out of the page. So the thumb will be pointing out of the page and the current and the magnetic field will be in this direction. So adding the arrows, this is anti-clockwise. And in this case, the thumb pointing towards the page, the magnetic field will be pointing clockwise. So these are the arrows, and the spacing between the curves. Generally, you should use a compass to draw these curves. Will be pointing clockwise. Now, if you have a coil or a solenoid, you must draw the field inside and outside the solenoid. So the inside, it appears as if they are parallel lines, so it is almost uniform, and the concentration of the field is at the center. And moving outwards, you create loops which go from one side. This will be the north pole of the coil, and the other side the field enters from is the south pole of the solenoid. and you get the direction also using the right hand grip rule. But first, let's talk about how to make the field stronger. You can use more turns of coil, you can use a stronger current or a larger current, or connect it to a battery with greater voltage or EMF, or bring the loops of the coil closer to each other. This will create a stronger magnetic field. Or you can insert an iron core. Now, using the right hand grip rule in reverse, now the fingers will represent the current and the thumb will represent the direction of the magnetic field. So if the current is moving upwards from the back, then moving downwards from the front, upwards from the back and downwards from the front, using the fingers, the thumb will be pointing to the right. So this side will be the north pole and the other side, the field will be going in, so it is the south pole. Or if the current is going upwards from the front and downwards from the back, upwards from the front and downwards from the back, the thumb will be pointing to the left. So this side will be the north pole and the other side will be the south pole. Now, to create an electromagnet, you turn a coil or wrap a coil around an iron core. It could be shaped as a bar or as a U-shaped magnet. You can create the north and the south poles by controlling the direction of flow of the current in the coil using the right hand grip rule. And you can increase the strength of the magnetic field of the magnet by increasing the number of turns, increasing the current using an iron core, not a plastic or a wooden core. The magnetic field will magnetize the iron and make the field stronger. Another use for an electromagnet is the relay switch. A relay is generally a coil connected to a circuit just next to a switch which is made of iron or a magnetic material connected to another circuit. So the symbol for a relay is a rectangle, which is the coil connected to a circuit, next to a switch, which is connected to another circuit, and there is a dashed box around both. So this whole thing is a relay. If the coil gets magnetized, it attracts the switch, so the switch closes the other circuit. Usually the current in the coil circuit is small and the current in the switch circuit is large. So we use a relay to control a large current using a small current, or we say that we use a small current in a circuit to control a higher or a larger current in another circuit. A circuit breaker uses electromagnets to work as fuses. You are not required to memorize the design of a circuit breaker, but you are required to memorize the function. It uses an electromagnet to open the circuit if the current gets too high. Same as a fuse, but using an electromagnet instead of a wire that melts. Now, if you place a wire carrying a current inside the magnetic field, for example, the wire here is in between two magnetic poles, north and south, you have two magnetic fields interacting. One from the wire, which is concentric circles, like the ones shown here, and one uniform field from the magnets. These two fields interact and create a force. So if you have one magnet by itself, it has one magnetic field. Once you bring another magnet next to it, you have two magnetic fields interacting, and there will be a force of attraction or repulsion, or there will be a motion. So you are frequently asked about why, when you place a current carrying a conductor or a wire inside a magnetic field with a current flowing, it experiences a force or it moves. The answer is due to the interaction between two magnetic fields, one from the current and one from the magnet. Now, if you have a certain direction for the magnetic field and a certain direction for the current, usually if they are perpendicular to each other, the force on the wire will be maximum in value. And the force will be direction to both, so in direction perpendicular to both the magnetic field and the current. For example, in this case, it will be upwards. So the force is perpendicular to the magnetic field is perpendicular to the current, and the current is perpendicular to the force. They are all perpendicular to each other. To get the direction of the force or magnetic field or current, we use something called Fleming's left-hand rule, where the thumb represents the motion or the force, the index finger represents the magnetic field, and the middle finger represents the conventional current, which flows from the positive terminal to the negative terminal if you have a battery. Now, using this rule, you can predict the direction of the field or the direction of the current or the direction of the force according to the question. Two will be given, one will be required. Now, if you are at 90 degrees to the magnetic field, if the current is perpendicular to the magnetic field, you will get a maximum force. If the angle decreases, the force decreases. The amount of newtons decreases. If the force or if the current is parallel to the field, there will be no force. So if the current is perpendicular to the magnetic field, you get force maximum. If the current is parallel to the magnetic field, the force is zero or no force. If you reverse the current, you reverse the force. If you reverse the magnetic field, you also reverse the force. Now, in certain situations, you will be required to point one of the fingers towards the paper or away from the paper. For example, if you have North Pole and South Pole like this, the field is an arrow that is inclined upwards. That means going into the page. So you point the index finger towards the page, toward the paper. And if the current is to the right, the force will be upwards. If the current is to the left, the force will be downwards. And you can experiment using this rule. Now, if you increase the length of the wire or the strength of the magnets or the current in the wire, all these will affect the force. These will increase the magnitude of the force. Increasing current, increasing strength of magnet, or using a stronger magnet, or bringing the poles closer to each other, that will also increase the strength of the magnetic field. Or you increase the length of the wire inside the magnetic field, the force increases. This idea is used in the simple DC motor, which is a coil, a square coil or a rectangular coil connected to current between the poles of a magnet. If you have a north pole and a south pole, the field is pointing from the north to the south, but one side will carry current into the page and one side from the coil will carry current out of the page. Using the Fleming's left-hand rule, if the field to the right and the current is outwards, the force will be upwards. So this side will go up, and the other side, if the current is into the page, the force will be downwards, so this side will go down. If you have two opposite forces with some distance between them, we call this a couple. This creates a moment or a torque. If you want to increase the moment or the torque, use stronger magnet, increase the current in the coil, or use coil with more turns, or insert an iron core. Now, the coil is connected to something called a split ring commutator. Without the split ring commutator, the wire will rotate until it becomes vertical and by inertia continues. But since same direction of current and field creates the same direction of force, it first goes one way and then it will go the other way. But we need the motor to keep rotating in one direction, so we connect it to a split ring commutator. The function of the split ring commutator is to reverse the forces. How does it do that? By reversing the current in the coil every half cycle to keep the rotation in one direction. This is the function of the split ring commutator. It reverses the current in the coil every half cycle to keep the rotation in one direction. Now, for a practical motor, you use more coils, more turns of wire, and curved magnets. An idea is about motor effect also is using the loudspeakers. The loudspeakers have magnets with a coil or coils inside them. When the current moves in one direction, there is a force on the coil in one direction that pulls the cone of the loudspeaker outwards. When the current is reversed, it pushes the coil and the cone of the loudspeaker inwards. If you connect the coil to an alternating current, the force keeps reversing direction and the motion of the cone keeps moving outwards then inwards, outwards then inwards. That creates vibration and compressions and rarefactions which produce sound waves. The last part in this section is about moving charges. If you have a moving charge and the charge is positive, you have a positive current in the same direction. And if there is a negative charge moving in one direction, the current is in opposite direction. Now, if you have a magnetic field and this magnetic field is perpendicular to the motion of the charge, you have a current and a magnetic field, so you can use Fleming's left-hand rule. So if there is a positive charge moving to the right, there is a current to the right. And if there is a magnetic field into the page, it is usually represented by an X. If it is going out of the page, it will be represented by a dot and a circle. In this case, it's into the page, so the force will be upwards. So this charge will curve towards the top of the page. But at this point, for example, the velocity is in this direction, so the force will be in this direction. It is always perpendicular to the current. So it creates a circular motion. So you might be asked, why is it a circular path? Because the force is always perpendicular to the motion of the charge. Now, if you have a negative charge and the field is still into the page, field into the page, index finger into the page, but negative moving to the right means current to the left. So the force will be downwards and it will move downwards in a curved path or circular path. Once it is moving outside the field, it will continue moving in a straight line. This also will continue in a straight line. If you have two wires with currents in the same direction, these are two magnetic fields interacting. They will attract each other. But if one of them is opposite to the other, there is still two magnetic fields interacting, but they will repel each other. So if currents in the same direction, they attract each other. If the currents are in opposite directions, they repel each other. Next chapter is called electromagnetic induction. This is generating electricity, not generating motion. In the last chapter, there was the motor effect. If you place a conducting material with current inside a magnetic field, it experiences a force. So the input here is current and magnetic field. The output was force or motion. In this chapter, the input will be magnetic field and motion, and the output would be electric current or voltage. So for inducing voltage or current, you need to move a magnet or move a wire next to a magnet. So if there is a relative motion between a magnetic field and a conductor, voltage will be induced, but in certain conditions. For example, if you move a wire across the field of a magnet, but if you're moving parallel to the magnetic field, there is no current. If you move it in and out along the same field line, there is no current. If you cross the field lines, if you place the magnet, the conductor between the field lines and you move across the field lines, this is called cutting the field, or that there is a change in flux, which is also called the field. A magnetic flux is a magnetic field. Since there is a change in magnetic field across the conductor, you're moving from one field to the next, to the next, to the next. This is called cutting the field, or there is a change in flux across the wire. This induces voltage. If you reverse the direction of cutting or reverse the direction of the change of flux, the current or the voltage is reversed. Now you can represent this another way by moving a magnet, not moving a wire, near a coil or a solenoid. If you move the magnet towards the solenoid, there is cutting between the magnetic field of the magnet and the coil wire of the solenoid. And if you move it away, there is also cutting, but in the opposite direction. So if you move one direction, the current will flow in one direction. If you move in the opposite direction, for example, away from the coil, the current will flow in the opposite direction. If you are required to demonstrate electromagnetic induction, always use the moving magnet and coil, because it creates a higher voltage, because it creates a higher rate of cutting. There is something called Faraday's law. If you move faster or use a magnet with stronger field, you have more lines to cut. This is called increasing the rate of cutting or increasing the rate of change of flux. The faster you move, the stronger magnet you choose, or the more turns of coil if you have a coil, the higher the rate of cutting and the higher the electromotive force or voltage you will induce. So the voltage induced in a conductor as it cuts a magnetic field or as there is a change in flux in the conductor increases at the rate of cutting increases or as the rate of change of flux increases. Now, to know the direction of the induced current in a straight wire moving in a magnetic field, we use the same three fingers of Fleming's left-hand rule, but we are using now the right hand. Using this right hand, the thumb will point towards the motion of the wire. The index finger will point in the magnetic field direction, and the middle finger is the induced current. So if you move a wire upwards, this is the direction of the motion, this is the thumb, and you have a magnetic field into the page, you will get a current pointing to the left. So the current will move in this direction. If you have a connection with a component outside this wire, the induced current will move from this side, which means this side is considered positive and this side is considered negative, and the wire now is considered as a battery. So we say that moving the wire, there is a change in flux or there is a cutting of magnetic field, which induces an EMF, a voltage of a power supply. And if you have a closed circuit, there is an induced current. And this induced current, you can get the direction of using the right hand rule, not the left hand rule. So if you already have a power supply and the current is already in the wire, use the left hand. If you want to get a current or induce voltage, use the right hand. Using this method to know the direction of the current or the magnetic field created by the current, if you move the north pole towards a coil, the current induced in the coil will be such that it will try to stop the magnet. This is called Lenz's law. Lenz's law states that the induced current due to cutting of magnetic field or due to change in flux opposes the change in flux or opposes the motion of the wire or of the magnet. So in this case, the induced current will create a force downwards. If you are moving upwards, there will be a force against your motion. If you move downwards, there will be a force upwards against your motion. Again, if you bring a north pole towards a coil, the current in the coil will create a north pole in its face to repel it. If you move a north pole away from the coil, the current will be reversed to create a south pole to attract it, to prevent it from moving away. It's always opposing the motion. So if you go with the south pole near a coil, the current will be induced so that there will be a south pole to repel it. If you go with the south pole away from the coil, the current induced will be so that there will be a north pole to attract it, always opposing the motion. This is called Lenz's law. So whenever there is an induced voltage or induced current, and you are asked about why did the voltage decrease, why did the current decrease after moving the wire or moving the magnet, you mentioned that the induced current is such that it opposes the motion, according to Lenz's law. Now, the idea of moving a coil inside a magnetic field and getting a current back is the basic idea of a simple AC generator. So there is a coil between two magnets, and the coil is rotated with an external force. You input kinetic energy, you move the coil yourself. You're not expecting it to move by itself. And you rotate it so it creates a changing flux or a change in magnetic field in the coil, which induces a voltage across the coil, and you can use this voltage to get alternating voltage or alternating current out of a generator. Now there are two rings here called slip rings. These rings are not the same as a split ring commutator. These rings are just so that the wire does not coil around itself or does not twirl around itself. It is used just to convert the current or to transfer the current from the coil to the outside circuit. It does not reverse current. It doesn't do anything except transfer the current from the coil to the outside circuit. Now, using the right hand rule, if there is a magnetic field from north to south, in this case to the right, and you move one part of the coil upwards, so section AB, according to the rotation direction, will move upwards, the current will be into the page, moving from A to B. The other side is moving downwards. So if the magnetic field is still to the right from north to south and the motion is now downwards, the current will be out of the page, so moving from C to D. Now eventually wire AB will move downwards and wire CD will move upwards, so the current will reverse. So if you are asked why does a generator create alternating currents, because each side of the coil sometimes moves upwards and sometimes it moves downwards. When you reverse the direction of the motion, you reverse the direction of the current. So the output of a generator is an alternating current, not a direct current. If you want to increase the voltage coming out of a generator, you can increase the area of the coil, so the magnetic flux will increase the number of turns of the coil, use a stronger magnet, or rotate the coil faster. This increases the voltage. Now you get maximum voltage when the coil is in the vertical or horizontal position. In the vertical position, the coil sides are actually moving parallel to the magnetic field, so there is no current. If you place it horizontally, the sides of the coil are actually moving perpendicular to the field. So you have, if the vertical position of the coil is now the start of the motion, you have zero voltage. If the coil is horizontal, you get maximum voltage. If the sides of the coil are reversed and it's again horizontal, it is maximum voltage but negative in the opposite direction. And whenever the coil is vertical, the voltage is zero. So vertical gives zero, horizontal gives maximum. But what about in between? In between, the angle of motion is neither parallel nor perpendicular. So perpendicular is maximum, parallel is zero, which means in between with different angles you will have different currents. That's why the current does not keep its magnitude. It increases, reaches maximum when the coil is horizontal, then decreases to zero when the coil is vertical, increases in the opposite direction to maximum when the coil is horizontal facing the other side, and so on. So why does the magnitude of the current vary? Because the angle changes the rate of cutting of the field. As the angle changes, the rate of cutting the field changes, so the induced voltage changes. Now, whenever you have two coils, one of the coils is connected to an alternating current and the other coil is connected to a voltmeter or will be used as an output device, connected to a lamp, connected to a motor, or connected to anything that is not a power supply. This is the basic idea of a transformer. Two coils, one is considered the input, the primary coil, and one is considered the output, the secondary coil, and usually there will be an iron core connecting them, or they are wound around on an iron core. If you are asked how a transformer works, you must say three sentences at least. The first sentence is that the alternating current in the primary coil, so the primary coil is connected to an AC supply, it must be an AC supply, because an alternating current creates a changing magnetic field. And the iron core is used to increase the strength of the field or transfer the field to the secondary coil. So the first sentence is that the primary coil carries an alternating current, and the alternating current creates a changing magnetic field, and the iron increases the strength of the field, or the iron core transfers the field to the secondary coil. And since the field is changing, there will be a change in flux or cutting on the secondary coil. This cutting will induce voltage on the secondary coil. You are not allowed to say that there is a current that flows from the primary to the secondary. They are not connected. And the iron is actually not connected to the wires. These wires are insulated. So you must mention magnetic field and cutting of magnetic field. You are not allowed to say two magnetic fields cut each other. This is a wrong sentence. It is the magnetic field of one coil cuts the second coil. The wire itself, not its field. So, if you want to increase the voltage across the output area, you increase the number of turns on the output area, which is called the secondary coil. This is called the step-up transformer. If you have a step-up transformer, it will have more turns of coil on the secondary part than on the primary part. The opposite, if you want to decrease the voltage, you will have less turns of coil on the secondary than on the primary. So the rule of the transformer is that the number of turns is proportional to the voltage. So if you calculate a ratio between the voltage of secondary to primary, it is equal to the ratio of number of turns of secondary to primary, or Vs over Vp equals Ns over Np. V over V is equal to N over N, and they are the same. If you have secondary at the top, they are on both sides, secondary on the top. If you have primary on the top, both sides should have primary on the top. Now, when transmitting electricity, you transmit electricity at a high voltage, so the output of any electrical power station would face a step-up transformer before the electricity is sent into the cables. So a step-up transformer is used to step up the voltage to increase the voltage. Why? For an ideal transformer, the input power is equal to the output power, or the primary power is equal to the secondary power. And power is equal to VI. So V primary, I primary is equal to V secondary, I secondary. Or if you rearranged, the currents secondary to primary is equal to primary to secondary in voltage, which means in a transformer, only in a transformer, the current is inversely proportional to the voltage. When you step up the voltage, the current decreases. If you step down the voltage, the current increases. This is an advantage if you use a step-up transformer, because if you use a low current, you are decreasing the heating effect of the current. So less energy losses or less power losses according to the equation P equals I squared R. If you have a constant resistance wire and the current decreases, the power also decreases. And there is no need to decrease the resistance. So if you need to decrease the power, you either decrease the current squared or decrease the resistance squared. Decreasing the current squared using a step-down transformer. Decreasing the resistance, you either decrease the length between a city and the generator, which cannot be done, or you increase the area, which means use wider wires, which will be more expensive. So using a step-up transformer decreases the current, so decreases power losses. And there is no need to use wide wires or thick wires to decrease the resistance, so it will be cheaper. Now, if you have a non-ideal transformer, the amount of energy lost is due to several things. One is called the eddy currents, or currents induced in the core. If the core is inside the changing magnetic field and it is made of iron, a conducting material, there will be induced current in the core, and the core does not actually transmit current to the outside circuits or to the secondary coil. So these currents are useless. They just heat up the core. So heat generated due to eddy currents in the core, this is one source of energy losses. But if you make the core out of sheets, laminated, with insulating materials in between, these currents will disappear. Because there is a poor conducting material, current cannot flow through a poor conducting material. The next source of energy loss is the leakage of the field. If you connect the core of a transformer like this to a coil on one side and another coil on the other side, half of the field of the primary coil is not used. Only one half is used. This is called flux leakage, or leakage of magnetic field. But if you create a core that takes the full shape of the magnetic field, you are prevented the leakage of magnetic field. So you also fix this problem of flux leakage. The last thing is the coil resistance. If you use coils of resistance of low magnitude or low resistance, you are decreasing the power losses in the coils. So technically, every energy loss problem is fixed in a transformer. That's why you can say that a transformer is a perfect device, or power in is equal to power out. If for any reason you find a question with a transformer that has, for example, 90% efficiency, use the equations of a transformer normally, and then at the end multiply by 90%, which is 90 divided by 100. or 0.9. The last chapter of circuits and magnetism is about other special components, which are the light-dependent resistor and the thermistor. A thermistor is a device that changes resistance according to temperature. If the temperature increases, the resistance of the thermistor decreases, and vice versa. If the temperature decreases, the resistance of the thermistor increases. The LDR depends on light, so if light intensity increases, the resistance of the LDR decreases. If you are required to state the names of the devices, you are not allowed to mention the initials of the device. So this is a light dependent resistor, not an LDR. And this is a thermistor. Okay, so a thermistor symbol is a rectangle with a spatula on top of it, and an LDR is a rectangle with two arrows pointing towards the rectangle. You can draw the circle or keep it without a circle. If you connect these in series with any device, if you change the environmental conditions, for example, for a thermistor in series with a lamp, if you increase the temperature, the resistance of thermistor decreases, so the current in the circuit increases and the lamp becomes brighter. And if you connect an LDR and you increase the light intensity, the resistance of the LDR decreases and the lamp also brightness increases. But if you use these in potential divider circuits and use a relay or something connected in parallel with part of the circuit, for example, in this diagram, we have a thermistor in series with a fixed resistor. If the temperature around the circuit increases, the resistance of the thermistor decreases, so the voltage on the thermistor decreases. But the voltage across the resistor increases. In a potential divider, if one voltage across a component increases, the other decreases, and vice versa. The relay is connected in parallel with the resistance. So the voltage across the relay increases and the switch is closed. So this works. This is a symbol of an electric bell. It's like a mushroom. So if you have a light-dependent resistor, for example, on the other side, we have here an LDR at the top and the fixed resistor at the bottom. So if light intensity decreases, the resistance of the LDR increases. So the voltage across the LDR increases. And the relay is connected in parallel with the LDR. So the voltage across the relay and the switch increases. So the switch works and the bell rings. These circuits can be used as automatic lighting systems or, for example, temperature or fire alarms. These are practical uses for these devices. The next device is a semiconducting diode. It's a device that allows flow of current in one direction. The symbol of a diode is an arrow drawn as a rectangle and a block in the face of the arrow, so the current can flow in this direction. It cannot flow in the other or the opposite direction. So the tail of the arrow must be connected to the positive terminal of a battery, and the head of the arrow must be connected to the negative terminal of the battery. If it is connected in reverse, there will be no current. If it is connected in the correct way, there will be current. A diode can be used as a rectifier. Rectification means changing alternating current into direct current. If you have one diode in the circuit, half the current will work, and when the current is reversed, it does not work. It keeps the current zero. So you will have a hump, which is half the wave of an AC current, of an AC voltage, then zero, then another hump, then zero, then another hump. Half of the voltage is not transmitted, or half the current is not transmitted. This is called half wave rectification. Half of the time the current is zero. If you want a full wave rectification device, you use 4 diodes in a diamond circuit. So you start with one point and you end with another point. These are connected to the output, which is required to be a direct current. So for example, you want the current always to flow in one direction to the right. So it must come from this side and go to that side. You draw the diamond circuit or the diamond wires, and you point the diodes so they point with the direction of the current. So it is going in from this part, so you point the diodes away from this part. And the rest, each two diodes opposite to each other will be pointing in the same direction. This is how you draw a full wave rectifier circuit, and the output will be connected to the left out terminals. This is the input of the device. This is the alternating current from the supply. So now you have an alternating current that is fully changed into direct current. So it will not be a hump then zero, a hump then zero. It will be all upwards in one direction. So this is the original current. It will be like this. All voltage will be in one direction, all positive or all negative. Now, one type of diodes is the light emitting diode. It has the same symbol, but with arrows pointing away from the diode. So it signifies that there is light coming out of an LED. Now there are electronic systems. We are not required to go in depth in all electronic systems, but we are required to know that electronic systems work using digital signals, not analog signals. The difference between digital and analog is that analog signals can take any value or can take any voltage or vary continuously. But a digital signal can only have specific values. For a binary system, it has only two values, which are high and low, or we call them 1 and 0. But it is not actually 1 and 0, it is just high voltage and low voltage. This is binary digital, but any digital signal, it can have more values other than high and low, but has specific values. An analog signal can take any value. So for an analog signal, you can draw a graph with a curve, continuous curve, but for a digital signal, you draw square voltages or square lines. The advantages of digital signals over analog signals is that digital signals can contain security codes, so it is more secure. They can carry more information if you use more bytes or more bits. They can travel faster, they have higher frequency and can send more data. And they can be cleanly regenerated. For example, if you have an analog signal like this, a voltage that varies like this, and then there was an induced current due to a magnetic field around the wires, then the signal got screwed up like this. You cannot clean this signal. But if you have a digital signal like this, and then you got noise over it, you can still know which parts were high voltage and which parts can low voltage. So you can regenerate the signal, but you cannot fix an analog signal. You can fix a digital signal, but you cannot fix an analog signal.
Now we're going to talk about atomic physics and radioactivity. First, we talk about the simple model of the atom. We have a central nucleus that contains protons and neutrons, and electrons that orbit around the nucleus in energy shells. If you want to compare between the charges of the electron to proton to neutrons, we have a magnitude of 1 to 1 for electrons and protons. They have equal magnitude of charge, but electrons are negative, protons are positive. Neutrons are neutral, so the net charge is 0. And comparing the masses, protons and neutrons have equal masses, approximately equal masses, and the electrons are almost 2,000 times lighter. So if we considered protons to neutrons 1 to 1, the electrons would be approximately 0. Now we go to nuclide notation. If you write an element in the periodic table, you write as a symbol consisting of 1 or 2 letters, then a number at the top which represents the nucleon number, which is the sum of the protons and neutrons, and the number on the bottom is the proton number, which is the number of protons or number of electrons in a neutral atom. Similarly, we use this notation to write symbols for electrons, protons and neutrons. So an electron would be E with a mass number or nucleon number 0 and a proton number which represents the charge -1. A proton has nucleon number 1, proton number 1. Neutrons have nucleon number 1 and proton number 0. in this table. Now we go to the idea of isotopes of the same element. For example, there are three isotopes of hydrogen called protium, deuterium, and tritium. They all have the same number of protons. They have same proton number, but different neutron or nucleon number. For example, for protium, it has no neutrons. Deuterium has one neutron. Tritium, it has two neutrons, but they all have one proton. And for a neutral atom, they have the same electron number also. Now, some of the isotopes are called stable isotopes and some are called unstable isotopes. For example, carbon 12 and carbon 14. Carbon 12 is stable, carbon 14 is unstable. It has more neutrons, or the number of protons and neutrons are unbalanced. The more you balance the number of protons and neutrons, the more stability you get, and the more you have protons and neutrons different numbers, or neutrons much more than protons, you will get an unstable isotope. Now, unstable elements can emit ionizing radiation, which is radiation that causes the atoms around the source of radiation to be either positively ionized or negatively ionized. A positive ion is an atom that loses electrons. A negative ion is an atom that gains electrons. And the kind of emissions from an unstable nucleus causes ionization around the nucleus. So radioactivity is a decay or the disintegration of a nucleus. A nucleus starts emitting particles or emitting energy. So it decays, so it disintegrates by releasing ionizing radiation. This kind of radiation is random and spontaneous. Random means it cannot be predicted which nucleus will decay at a certain time, and spontaneous means you cannot control the rate of radiation or the rate of emissions by changing the environmental conditions. Now we need to differentiate between alpha, beta, and gamma radiations, which are the types of ionizing radiation emitted from an unstable nucleus. They are all emitted from nuclei, not from the atom as a whole. It's from the nucleus only. So for an alpha particle, it's a helium nucleus or two protons and two neutrons. Beta particles are one electron emitted from the nucleus. Gamma radiation is an electromagnetic wave released from the nucleus. As for the atomic mass and atomic charge, which represent nucleon number and proton number, we write alpha with 4 at the top and positive 2 at the bottom. We write beta with 0 at the top and negative 1 at the bottom, just like electrons. And gamma radiation has numbers 0 and 0. As for the speeds of emission, the alpha is the slowest particle, beta is moderate, and gamma radiation is the fastest. It travels at the speed of light in vacuum and in air. And when they travel, they have a penetration power, which is the limit of their distance traveled in air. In air, alpha particles have a range of up to 7 centimeters or 5 centimeters in air, according to the density of the air. The more dense the air, the less distance it can travel, because it causes a lot of ionization, so it has a large ionizing power, so it loses energy very quickly. Beta particles are less ionizing, so they can travel much longer distances. They can travel up to 10 meters, but not all of them travel with the same speed. And gamma radiation, they travel in terms of kilometers. They travel very long distances in air. But you can stop alpha particles using thick paper or a thin metal foil. You can stop beta particle using a thick metal or 5 millimeters of metal, maybe aluminum. Gamma radiation, you can reduce the energy of the radiation to half by 15 centimeters of lead or concrete. So you need very thick walls of lead and concrete to decrease gamma radiation to be ineffective or not harmful. And it is the least ionizing, that's why it can penetrate through heavy materials. Now, as for the deflection in an electric field or in a magnetic field, if you have an electric field caused by two plates, positive and negative plates, The alpha particle will be deflected towards the negative plate because it is it's positively charged and it is attracted to the negative side. Beta particles are deflected towards the positive plate because they are negatively charged, so they are attracted towards the positive charge. Or we can say that opposite charges attract. As for gamma radiation, it is uncharged, it has no net charge, so it is not deflected by electric fields. As for magnetic fields, we always use Fleming's left-hand rule to get the direction of the deflection. If you have an alpha particle traveling in a certain direction, you say that the current is in the same direction because it is a positive charge and current flows in the same direction as positive charge. As for beta particles, you say that the current is flowing opposite to their direction. So if a beta particle is moving to the right, the current is actually to the left. So in this case, you have a magnetic field going into the page, so the index finger is pointing into the page. If an alpha particle is moving to the right, you say that the current is to the right. You will find that the deflection will be upwards. And if the field is still into the page, but the current is to the left against the beta particle will experience a downward force. And again, since gamma radiation is uncharged, it has no current, so it is not affected by magnetic field either. So no effect on gamma radiation with electric fields or magnetic fields. Now, for the deflection amount for alpha and beta particles are much heavier, so are much more difficult to deflect. So they deflect small amounts of deflections or small angles. But beta particles are very light, so a small force would cause them to deflect greatly. So the deflection of alpha particles is much smaller than the deflection of a beta particle. So beta particles deflect much more than alpha particles. As for the nuclear transformations caused by the alpha, beta, and beta decays, they always cause the radioactive material to change into a new material or a new nucleus with a different proton number. So if you have an element called X with a nuclear number A and proton number Z, it will change into a new nuclide or new element called Y, for example, and this element has less protons and less nucleons. So you lost 2 protons and 2 neutrons as an alpha particle. So the proton number decreases by 2 and the nucleon number decreases by 4, or the neutron number decreases by 2. And you have the alpha particle, which you should memorize always with a top number, nucleon number 4 and proton number 2. As for beta decay, there is a change in the nucleus where a neutron changes into a proton and releases an electron as a beta particle. So the proton number increases by 1 and the neutron number decreases by 1. But the nucleon number does not change. The amount of particles in the nucleus does not change. So the nucleon number does not change, but the proton number increases by 1 and the beta symbol is 0 and -1. As for gamma emissions, there is no change in the nucleus when you release a gamma radiation wave. So there is no equation for gamma emission. Now we're going to talk about radiation detectors. We have 2 types of detectors. The first detector is called the GM tube or Geiger-Müller tube. It is always connected to a counter or a count meter. It reads how many radiation particles are emitted per unit time, per second, or per minute. So you will always find a unit called count per second or count per minute, or another unit called becquerel. This means count per second. As for the second type of detector, we have something called the cloud chamber, which has ionized gas in the area of a chamber, of a cylinder, of a small cylinder. If the radiation source emits alpha particles, the clouds in the chamber appear to be straight lines. If it emits beta particles, it will be curved lines. And if you have gamma radiation, you will not have specific shapes, you will have random shapes in the cloud chamber. Now we talk about background radiation. In any room or any event, you will find always a small amount of radiation, even though you will not have a radioactive source in the room. You will still take a reading from the GM tube, which is probably about 30 counts per minute, 25 counts per minute, maybe 40 counts per minute, around something that is more radioactive. And this kind of radiation, it is not caused by uranium or plutonium or anything like that. It is caused by the radioactive gases in the atmosphere released from underground rocks and radioactive materials that are still in the earth crust, like the uranium and plutonium that we did not dig up yet. They release gamma radiation which can penetrate the rocks and reach the surface. Also, medical equipment in hospitals use X-ray machines, and they use gamma radiation to sterilize their equipment to kill bacteria and viruses. Also, there is nuclear power stations that use nuclear materials to generate electricity. We talked about that in chapter 6. And if there is a source of radiation that is not on the planet, it is called cosmic radiation. This is radiation that comes from outer space, from the stars around us and the planets around us. So these are the sources of background radiation, and this is the type of radiation you would measure even though there is no radioactive source in the room. Now, how to find out the amount of radiation and the type of radiation using detectors? You can use a GM tube and use the information about how to stop each type of radiation. For example, if you have a count rate of 2000 counts per second between the source and the detector, and then you add a piece of paper or thick cord between the detector and the source of radiation, and suddenly the count rate decreases, that means there was alpha particles in the region and they did not reach the detector when you added the paper or the piece of cord. So there is alpha particles present in the radiation. If the number did not decrease by much, then alpha particles are absent. They do not exist. They are not emitted from the source. If you add an aluminum sheet, which is 5 millimeters thick, this could stop the beta particles. So if the number decreases after adding the aluminum sheet, you know that there was beta radiation present in between the source and the detector, so that the radiation source emits beta particles. If the number did not decrease again, then beta particles are absent or are not emitted from the source, and the rest of the radiation is background and gamma radiation. So before placing the source in front of the detector, first read the background radiation, then you add a piece of paper, a thick paper or an aluminum foil to see if the number decreases, then there was alpha particles. If the number does not decrease, then alpha particles are absent. Then you add an aluminum sheet that is at least 5 millimeters thick. So you detect if the number changes. If the number decreases, the beta particles were present and were absorbed by the sheet. If the number does not decrease, they are not present, and the rest of the radiation is gamma radiation and background. And you can remove background from each count reading after adding the paper or the aluminum sheet to correct for background. Now we're going to talk about half-life. Half-life is a time period where the activity decreases by half. So dividing the initial activity by 2 and see which time how long it takes to decrease to half. This time is called the half-life. So it is a time for the activity to decrease by half, or it is the time for half the nuclei in an unstable element to decay. So each time a half-life passes, the new value of the activity decreases by half, and so on. So this is the shape of the graph for the activity corrected for background. If you have a question where there is no graph that you can use to find the time, if there is a graph, you take the initial value, you divide it by 2, and you get the new value and go on the graph to see which time it takes. But if you don't have a graph, and for example you have the half-life and the total time of the experiment, first you divide the total time by the half-life to get the number of half-lives. and then you take the initial radiation. For example, in this question it was 240. This is the initial activity, and then you divide it by the number of half-lives. For example, here, if you divide 12 years, which is the total time, by 3, you get 4 half-lives. So you divide by 4, so you divide by 2, sorry, 4 times, because you have 4 half-lives. So this is 120, then 60, then 30, then 15. This is the final reading on the count meter or the GM tube, because we have 4 half-lives. You would divide by 2 4 times, or we divide by 2 to the power of 4. Now, if you have background in the question, you must remove the background before calculation. So if you have a background of 30 and the initial reading was 230, you first remove the 30 from the initial activity. You get 200. And if you have the final activity, you just divide by 2 until you reach the final activity, but you must remove the background from the final activity as well. So 55 minus 30, that is equal to 25. So you go 200 divided by 2, that's 100, divided by 2, that's 50, divided by 2, that's 25. We reach the final activity in 3 half-lives. Now, if you have the total time, you say that the half-life is the total time divided by the number of half-lives. So you get 25 minutes as half-life here. If you have the half-life and you want the total time, you multiply the number of half-lives by the half-life itself, so you get the total time. Now, if you get a graph that does not keep decreasing on the activity axis or the count rate axis, if it becomes horizontal eventually, this means that this level is the background radiation and this graph is not corrected for background. So the first step, you get the initial activity and you subtract the background, which is the horizontal level. Then you divide by 2 to get the new value after 1 half-life, and the next step is adding the background after dividing by 2, and then using this value with the background to see the time it takes. So this is the half-life you get. So a question like that would have 3 or 4 marks. In case of the corrected activity graph, it would only take 1 mark if you have no background. So because you have 4 steps here. First, you take the initial value and subtract the background, then you divide by 2, then you add background again, and then you use the graph to get the time. But without background, you just take the initial value, you divide it by 2, and get the time directly. As for the uses of radioactivity, you can use a radiation source, maybe a beta emitter, always a beta emitter, because the thicker the metal, you get the less beta particles that can penetrate it. So the thinner the metal, more beta particles will penetrate it and reach a detector. So you can use this as a thickness gauge or a thickness meter in metals in factories, but it is also always a beta source. We can use them as tracers. Maybe gamma emissions is not suitable because gamma can penetrate metals very easily, and alpha particles are not suitable again because they cannot penetrate metal pipes. If you have a pipe that is cracked or has a leak in it or a hole in it, the liquid or gas will be spread or will leak outside in the soil, so the radiation can reach the surface from that hole. Now, if you need a radiation type that is affected by the metal thickness, you also need to use a beta emitter, and in this case you need short half-life. But in a factory, you need a long half-life, so you do not have to replace it. But in a tracer, you need a short half-life in order to finish the investigation about finding the leak quickly, and then you can circulate the water again, or the liquid again, or the gas again, so the public can use it. So for public use, you need a short half-life. For manufacturing, you need a long half-life, so you do not have to replace the element many times in 1 year. They also use radiation in radiotherapy and chemotherapy. They use radioactive isotopes injections or tablets that are swallowed to kill the cancer cells or the tumors, which are basically mutated cells caused by radiation. But you can also kill cancer cells using radiation. Usually it is a gamma emitter because it has the least ionizing effect, so it will cause less damage than an alpha emitter or a beta emitter. We also use this in sterilizing medical equipment in hospitals. They can kill viruses and bacteria. As for archaeology, we use carbon-based detectors, or a detector that compares the radiation of a dead body and a living body, and compare these amounts of radiation on the graph of half-life for carbon. Sometimes it's called carbon dating. So you date something that died a long time ago by the amount of radiation that it is emitting compared with a living similar object. For example, a chair, it is made of wood. I will compare its emission with the emission from a living tree. Or a skeleton of a dead body, you compare it with the body or the emission from a living man. Another use for radiation is in smoke detectors, but smoke detectors we use alpha particles. We can either set up a detector as a source of alpha particles placed in front of a metal plate, and the alpha particles move towards the plate. As the particles move, they are positively charged, so they create current. When smoke enters in between the source and the plate, the alpha particles ionize the smoke and cannot reach the plate, so the current decreases. Another way is releasing alpha particles in a certain direction, and the smoke then is detected. When the alpha particles ionize the smoke, there is a plate here and a plate there, positive and negative charges. When there is a positive ion, it is moved towards the negative plate, and when there is a negative ion, it moves towards the positive plate. So the current is created when the smoke is detected, or the smoke blocks the current when it is detected. But we use also alpha particles because they have high ionization. We can use that high ionizing power to detect the current or the change in current. Now, for the dangers of ionizing radiation or radioactivity, ionizing means you can change the structure of an atom. If you change the structure of DNA in a cell, now the cell has no function and it is considered a cancer cell, or it can cause mutation. It can cause the cell to function differently in the body. Now it is not doing its own function, which causes damage to the body. For beta and gamma radiation, they have very high speeds, which means they have high kinetic energy, which means they can heat anything around them. So it may cause burns, skin burns, or it can cause the cataract of the eyes to dry up and turn white. Or they can also cause a cancer or mutation in the cells. Now, for nuclear power stations, if an explosion happens due to the inability to cool a reactor, the reactor explodes and radioactive materials are spread across the area. This is called contamination. If the radiation leaks without explosion, if the radiation itself goes out into the living organisms, this is called irradiation. So irradiation is radiation leaking out. Contamination means there is radioactive elements inside the living organisms, or inside the soil, or inside the buildings. For safety, we use long tongues to hold radioactive materials, and we wear protective suits that are lined with lead. We also use any air supply or oxygen tanks or air tanks while performing any experiment, or using any radioactive materials in a power station or anything like that, to prevent inhaling any source of radiation, to prevent contamination inside the body. And nuclear waste is usually contained into thick lead containers or thick concrete rooms or concrete walled rooms underground to prevent radiation from reaching the surface, since lead and concrete can absorb beta particles and alpha particles easily, and gamma radiation is always the least ionizing, so it is the least dangerous. So it can penetrate the lead walls or the concrete walls, but it will have much less energy after passing through a large thickness of lead or concrete. Now we talk about the structure of the atom. There is something called the alpha scattering experiment or the Rutherford experiment, where alpha particles are directed towards a thin gold foil. The observations of the experiment are related to specific conclusions. So the first observation was the unexpected observation that most of the alpha particles pass straight through the foil without damaging it. This means that most of the gold foil atoms are empty space. That's why most alpha particles went through them. The second observation that some of the alpha particles were deflected away from their original direction. This means they were repelled. But since alpha particles are positively charged, they must have been repelled by another positive charge. So within the empty space of the atom, there is a concentrated positive charge that repelled the alpha particles. And very few alpha particles rebounded backwards. So rebounding means you met something that is much heavier than you are, so there must be a heavy central core inside the atom. So within the atom there is a central point or central object that is positively charged and has a very heavy mass. But why very few particles rebounded? Because that heavy mass occupies a very small space, or it has a very small volume. We call it a tiny core. So we deduced from this experiment that most of the atom is empty with a very tiny core that is positively charged and contains most of the mass of the atom. No mention of electrons or the type of particles inside that core, which is later, many years later, called nucleus. Now we're going to talk about the nuclear reactions we use in a reactor, or the nuclear reaction that occurs in a star. We have nuclear fission. Nuclear fission is the splitting of a nucleus by adding a neutron to make it more stable. And the nucleus splits into two lighter and more stable nuclei and releases neutrons in the process. These neutrons eventually hit other nuclei of the same heavy element or initial element and cause more fission reactions. This is called a chain reaction. For example, in this diagram, one fission reaction released 3 neutrons, so one reaction will cause 3 reactions, and each of these will cause 3, so you will get 9 and then 27 and so on. This is called a chain reaction. So splitting of a nucleus to create lighter nuclei and release energy, this is called fission. And in this process, the total mass of the products of the reaction is actually less than the original mass of the reactants themselves. That means that the mass decrease, so there is a defect in mass, and this mass is converted into the kinetic energy of the released particles. This is what causes the heating effect. As for fission reactors, they are mainly consisting of fuel rods that are made of uranium or plutonium, control rods that are in between. If you insert the control rods in between the fuel rods completely, you are shutting down the chain reaction. If you remove them, you have to restart the reaction, but then you have a high rate of chain reaction, then you have much more energy released. As for the rods are placed in something called the moderator, which is mainly graphite. This is used to slow down the released neutrons in the reaction to enable the chain reaction. So the released neutrons are very energetic. They have high kinetic energy, so they may go right through the nuclei and not cause the fission reaction. To slow them down and they settle inside the nucleus and make it more stable, you need a moderator which is made of graphite. And the whole reactor is submerged in water, and we use heat exchange to release the heat from the reaction into the water. Then the water turns into steam, and we blow it through a pipe towards a turbine, which rotates a generator to generate electricity. The other type of reaction is the nuclear fusion of two light nuclei joining together or combining together to form a heavier nucleus. For example, two hydrogen isotopes that join together to form helium, a helium nucleus. So we say two light nuclei combine to form a heavier nucleus, releasing energy. This is also due to defect in mass. The mass of the helium and a released neutron is less than the total mass of the two hydrogen nuclei. So the released mass or the defect in mass is converted into the kinetic energy of the products and the heat radiation emitted from the reaction.